Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. In this lecture, we are going to see the following topics: the sharpness of resonance, power dissipation, quality factor or Q factor, and Helmholtz resonator. We are now familiar with the concept of resonance because that is the prerequisite for this lecture. The resonance occurs when the driving force or the driving oscillatory force matches with the natural frequency of the oscillating system. The amplitude of oscillation becomes maximum at resonance. With this idea, in this lecture we are going to see the concepts related to the resonance, especially the sharpness of the resonance peaks. What is resonance? We are now familiar with. When the resonance occurs, how the resonance frequency makes the system oscillate with the natural frequency, that is determined by the sharpness of the resonance curve. So, let us see the graphs which we have seen already when we learnt the resonance for understanding what is the meaning of sharpness of resonance peaks. Let us quickly understand what is the meaning of resonance. The frequencies at which the response amplitude is a relative maximum are known as the system's resonance frequency. At resonant frequency, small periodic driving forces have the ability to produce large amplitude of oscillations. This is because the system stores oscillatory energy in it. Now, how the peak occurs at resonance? Let us have a look at the sharpness of the resonance peaks, and this is a model graph which explains about how the sharpness of the resonance peak appear. This gives us a basic idea of the sharpness peak that is occurring at the resonance frequency. Here the resonance frequency is marked as F0, and all the three which we have taken as models have the maximum, the local maximum at F0 only, and this case has a small damping, that is why the amplitude has a maximum value. This second graph has the medium damping, which is marked here in red color. Because the damping is present and it is of a medium value, and the amplitude is slightly less, and this shows, the violet color graph shows a heavy damping. This also has a local maximum at F0, but the amplitude seem to be very less. So, this has given us a basic idea of how the sharpness of the resonance peak could occur. As the damping becomes lesser and lesser, the amplitude shoots up to a higher and higher value, and that narrows down the width of the resonance peak, and that is also shown in the diagram which we have seen. We will see such similar diagrams for our discussion further. So, we have got the basic idea about the relation between the amount of damping and the sharpness of the resonance peak. This has got a greater importance as far as the resonance occurrence is concerned. This has got lots of impact or implications on the way in which the resonance could occur. Let us see further what are the other factors which could govern the sharpness of the resonance peak. This sharpness is better measured by a term called Q factor or quality factor. It is referred as quality factor in general. There are few technical definitions for Q factor. The Q factor is a unitless quantity. One such definition we could take up for our discussion here, which is Q is equal to the ratio of omega naught to del omega. Here omega naught is the resonant frequency and del omega is the bandwidth at half power maximum. This relation seems to be very simple. It is a ratio. In the numerator we have the resonance frequency itself. Here it is mentioned as the angular frequency omega. We can even take the linear frequency f also, but for our discussion we have been taking the angular frequency which readily appears in the expression for simple harmonic motion. The omega term appears in several occasions, so we take it up for our discussion as such, and the denominator has the del omega, which is the width, we call it as bandwidth. It is not taken at any point, at a particular point it is taken, that is half power gain, half power width it is called. We will see further what is the meaning of half power. So, we have got a very simple definition for the term quality factor. It is a unitless quantity because the numerator and denominator they have the same term frequency. The numerator is the resonance frequency and the denominator is the bandwidth expressed in terms of frequency. So, it is a unitless quantity. With the help of this Q factor, we will be able to measure the sharpness with a numerical value. So, this Q factor gives us an idea about the sharpness of the curve. So, hereafter we will give importance to the Q factor only whenever we want to discuss about the sharpness of the curve. Sharpness is a very generic term, but when we say Q factor, it is a quantified value, it is a measure of the sharpness curve. So, we will be able to handle this Q value and what are the areas in which this Q factor appear, we will see one by one, and this graph further gives us some idea about the way in which the Q factor is calculated. We are now familiar with the expression. The numerator is omega naught, which we have here, which is the resonant frequency, and the denominator is the del omega. There are two curves taken up for discussion which have two different bandwidths del omega. So, for our reference we will keep the formula also next to us. So, this is the formula. In the curve which has got a very high power, for the discussion sake we have taken the power in the y axis and the frequency on the x axis, and for the weak damping or very less damping the Q factor will be very high, which is understood from the equation itself. The omega naught is same for both the curves, for the curve which is shown in brown color and also for the curve which is shown in blue color, the omega naught is the same. So, the numerator is the same, the denominator decides the value of Q for both. In the case of the very weak damping, the Q value is high because the denominator is very less, and we take this as the off power width. Why off power we are taking? It is done as a standard practice. We want at least half of the power to exist when we want the bandwidth to be calculated. So, that is taken into account. This del omega is measured at half of the power for this brown graph, and for the blue graph which has got a very heavy damping, the Q value is very low because the del omega term is high. It is a very large value, it is broad. See this, for this blue color, this is a local maximum of power maximum, and half of it value is taken here to find out the bandwidth. So, the sharpness of the resonance curve now is quantified in terms of the Q factor, the quality factor. Higher the Q factor, then the bandwidth is lesser, so the damping will be very less, and the reverse is true for when the damping is very heavy, the amplitude or the power is very less and the spread will be more, the denominator bit bandwidth will be very large and the Q factor will be very less. So, we can keep one thing in mind, higher the Q value, higher will be the power or higher will be the amplitude, and its equivalent damping is less. So, this idea when we have in mind, we will be able to correlate things better. Now, why this off power is taken? It is a standard practice. We want at least half of the power to exist when we do the measurement. So, it is done. Suppose we take the amplitude on the y axis and as usual the frequency on the y axis. How to find out the off power? In that case, we cannot simply take the value 1 by 2 directly. We have got an explanation for it. Let us see that explanation. When we take the amplitude on the y axis and the frequency on the x axis, I have just taken only one graph for the discussion. When we have the power, we can directly take half of the power, the maximum power, half of it we can take, and at that point we can find out what is the width, what is the spread, that is called the bandwidth. But when it is done for amplitude, we cannot take it that way. There is a value 0.707 that gets preeminence. How this 0.707 comes is explained here. The power is actually proportional to the square of amplitude. We want the power, half of the power. So, we have the amplitude divided by square root of 2, then only this will have the off power. So, now instead of 2 in the denominator, we have the root 2 because it is amplitude now, and we have a divided by 1.414 as the term. The 1 divided by 1.414 is 0.707. So, in general the off power gain when it comes in the form of amplitude has to be taken at a point where the maximum amplitude is multiplied with 0.707 value. It is called off power maximum again, but we have to multiply it with the value 0.707, or it is in simple terms the a divided by root 2. Now, at that point we have to take the bandwidth, and this bandwidth will be appearing in the denominator for the expression we have for Q factor, and this is also shown here in decibel. In decibel scale, how to take? It is the 3 times the decibel, the maximum decibel value has to be reduced, then we will have the off power maximum, off of the maximum power we will have. So, we have several methods to find out the bandwidth. If it is the power taken in the y axis, directly off of the value. If amplitude is taken, then the maximum amplitude multiplied with 0.707, Suppose if it is taken in the decibel scale, 3 decibels we have to reduce, at that point we have to take the bandwidth. So, this is how we have to find out the bandwidth, and the resonance has got lots of applications also. Before we get into the applications part of the resonance, we will further learn how the Q factor is related to the damping and how the Q factor is related to bandwidth. Actually, by looking at the graphs itself we would have understood, but anyway to have it in our mind registered, we will see them as the relations between Q factor and the bandwidth and also Q factor and the damping. Basically, the Q factor is defined as the ratio between the resonance frequency and also the bandwidth. It has got a typical technical definition like 2 pi multiplied with the ratio of maximum energy stored to the energy lost per cycle. This is the actual definition for the Q factor. When we try to derive what is the final expression we have for this term, the 2 pi multiplied with the maximum energy stored in the system and energy lost per each cycle, we will end up getting this value itself. So, we will not be giving importance to the mathematical simplification, but rather we will be able to use this final equation Q is equal to omega naught divided by delta omega. But nevertheless, we will see why this definition is given. In the resonance, actually it is a damped oscillation happening at the natural frequency. So, there will be the energy stored in the system, and at each cycle there is energy lost. Though there is energy replenished, we periodically give the energy at its natural frequency, because the damping is present already, there is a energy loss happening at a particular at the same period. So, there is energy replenished, there is energy lost and each cycle. So, there is a maximum energy stored in the system and it is periodically lost because of the damping present in the system, and again it is periodically replenished also, and definitely there will be a particular amount of damping, because if there is no damping then the resonance amplitude will shoot up to infinity. This concept we have already learnt in the earlier episodes. So, with the damping only we will have a maximum amplitude. If there is no damping, then the amplitude is shooting up to infinity. This is familiar to us. So, with the presence of damping only we could define the Q factor, and we have defined it in this way, and we have got a simple final expression which we have already used. Now, we will see the relation between the Q factor and damping. The Q factor determines the qualitative behavior of simple damped oscillators. A system with low quality factor, maybe Q less than half, is said to be over damped. A system with high quality factor or the Q factor which is greater than half is said to be under damped, and a system with an intermediate quality factor, say exactly half, then it is said to be critically damped. The over damped, under damped, critically damped, all these factors or these terminologies are very familiar to us because we have learnt about them already, and in terms of the quality factor also we can classify the damping. So, the quality factor has got a direct link with the amount of damping present in the system. Not only that, the quality factor has got the relation with the bandwidth, that also we will see. What is the relation between the quality factor and bandwidth? Higher the value of Q, lower the value of bandwidth, and the next statement, lower the value of Q, higher the value of bandwidth, which is very well explained by the diagram shown here. See, the amplitude is taken in the y axis and the frequency, angular frequency, is taken in the x axis, and the bandwidths are shown. this for the quality factor 1, here the quality factor 1 is marked for this graph, the bandwidth seem to be very large. So, lower the Q value, larger the bandwidth, and higher the Q value, lesser the bandwidth becomes narrower and narrower. So, Q factor has got a link with the bandwidth also, not only with the damping which we have seen, it has got a link with the bandwidth. So, Q factor is a very important factor. Now, we will see two terminologies called selectivity and sensitivity, because we are talking about the resonance. In the case of tuned circuits, the resonance is very important. We will have to select a particular frequency at omega naught by varying the factors, and also there must be a sensitivity. What is the meaning of these two terms? We will see them by looking at this graph. In the resonance tuning systems, a broader bandwidth gives good selectivity and a sharp peak at resonance gives good sensitivity. What is the meaning? These are actually higher order terminologies, but we should be able to keep them in mind when we learn about the resonance curves in which the tuning is used. See here, at this resonance frequency we need to choose the system to vibrate. When we narrow down the width by choosing a very high selectivity, very high way of selecting it, then the width will be lost. When we lose the width, particularly selecting the frequency is very difficult. So, we have to strike a balance between the selectivity and also the sensitivity. Sensitivity is related to the peak, that means the narrow down of the width. Selectivity means we need to have an appreciable width, the broadening of the curve. So, we have to be very careful while designing the tuning circuits where the resonance is used, so that we are able to select the frequency and also we are having the appreciable sensitivity also. So, we have to strike a balance between the two. When we learn about the tuned circuits, when we learn the concepts, these two terminologies will become very important. So, this has given us some idea about the two terms selectivity and sensitivity. Now, we will move on to the next concept for discussion. It is the Helmholtz resonator. We will see what it is. A Helmholtz resonator or oscillator is a container of gas, normally air, with an open hole. The hole will be in the form of neck or port. It was first designed by Hermann von Helmholtz in the year 1850. A volume of air in and near the open hole vibrates because of the spring action of the air inside. The common example for Helmholtz resonator is an empty bottle. The air inside vibrates when we blow across the top. Mild blow itself will produce a resonance to occur in the air column that is contained in a container. So, that is what is called Helmholtz resonator. We will see how it looks like. See, this is how the Helmholtz resonator look like, and this is the principle behind that, and this is the neck of the bottle. So, here it is the bottle itself is shown, and when we blow air we will be giving all the frequency, possible frequency, which one of such frequencies will match with the natural frequency of the air that is contained inside. Mostly it will be kept in the atmospheric pressure. When we blow, there is a variation happening and it will match. So, that is why it is having the spring action. The air is getting compressed and then it will become rarefied, and the movement, up and down movement of the air that is trapped here will happen, that will match with the natural frequency. The frequency which is available outside will match with the natural frequency, and that will make the object vibrate. This is the example for the Helmholtz resonator. These are all metal bulbs. Each bulb has got its own resonance frequency. The size of the bulb decides the resonant frequency. We will see how the frequency depends on the volume and also the neck size. This is the relation for that. See, this is the typical Helmholtz resonator. This is the expression for the resonance frequency. The resonance frequency is proportional to area of the opening port divided by two terms in the denominator, volume of the cavity and length of the opening port, and each term has got its own implication, and accordingly the resonance frequency is chosen. That is why we need to vary the volume of the cavity for a particular frequency of resonance, and also the length of the opening port and area of the opening port. So, these are the three terms which will decide the resonance. See, that is why we have various lengths and size, the opening size and also the volume. These are the three factors which govern the resonance frequency of the Helmholtz resonator. Why should we study about the Helmholtz resonator? This has got lot of application. I would like to mention some of the applications here, so that we could appreciate where all this Helmholtz resonator is used. Helmholtz resonance finds application in internal combustion engines in intake system, because it has got a piston and cylinder combination. The Helmholtz resonators are used in motorcycle and car exhaust to alter the sound of the exhaust note, and for difference in power delivery by adding chambers to the exhaust as a sound absorber, or we call generally for the two-wheelers and motor vehicles, we have a exhaust system which absorbs the sound, which takes the sound within itself and it is not heard outside much. So, for that the Helmholtz resonator is used. Not only that, in acoustics of auditoria and building, Helmholtz resonators are used in architectural acoustics to reduce undesirable low frequency by introducing suitably the resonators inside. And also Helmholtz resonators are used to build acoustic liners for reducing the noise of aircraft engine. Normally when aircrafts fly above a particular building, it will be heard inside. When it matches with the natural frequency of the room size, then the sound will be maximum. To reduce that, we can have the Helmholtz resonators implanted inside the auditorium or the rooms or the location, so that absorbs the sound and the resonance will be contained within the Helmholtz resonator itself. So, we have learnt about the Helmholtz resonators and also the applications of Helmholtz resonators. Before we end this lecture, we will see the summary of today's lecture. In this session, we have seen the concepts of sharpness of resonance, the power dissipation, the quality factor or Q factor, and Helmholtz resonator. Before we end this lecture, we will also check our understanding by answering these questions. What is Q factor in resonance? Define bandwidth of resonance peak. Discuss the relation between the Q factor and damping. Discuss the relation between Q factor and bandwidth. Discuss about the Helmholtz resonator and mention few of its applications. So, with this I would like to wind up this lecture. Thank you for watching.